Hey everybody, it's Dr. Jensen with CCJ 3701 Research Methods. This is kind of the last part of our linear regression lectures. We got a little cut off. I went a little too long and wanted to make this a little bit larger so you could see it better. So this is our output that we had run in trying to understand the question of knowing your political party, predict how many hours of TV a person watches per day. Okay, so our output we got to predict how much TV you're watching was right here. So here's the B, and we got the negative 0.129. It is a highly significant variable, and we got an R squared up here. It's kind of a small number, which we'll talk about later. But once you get output, you know how your variable is measured, and you've coded it in some way you can interpret, you can start having all these results. So let's start with the B, or the slope. So usually people start with the significance level, which this one's triple zeros. Our little p-value is less than 0.0001. So that means it's a highly statistically significant relationship. I have a less than 1% chance of it not being true. So we can feel confident that these two things are related. Knowing your political party does help me predict how much TV you watch. So moving on to the slope, or B. The slope, remember from our lecture, is the size of the average difference from the dependent variable that corresponds with a 1 unit difference in the independent. Okay? And here's our famous little formula we have. All right? So for every 1 point increase in X, or political party, I get this change in my TV watching in Y, okay, in my dependent variable. So you could literally write that out in English. For every 1 point increase in political party affiliation score, going from 0 to 7, there would be a predicted negative 1.29 hour decrease in the number of hours per day someone spends watching TV. Or 1.29 of an hour, or 60 minutes, would be approximately 7.2 minutes. Okay, it's a highly significant relationship. We're going to come back up to the top of the document over here. We can be confident assuming there is an actual relationship between it. Let's go to the constant, okay? We go back to the constant, which is over here, okay? Our constant was 3.327, okay? So remember, the constant is what the average starting point would be, or what we would expect most people's TV watching to be on average, okay? We call that the y-intercept, or the A. The predicted value of the dependent variable when the independent variable is 0, so not knowing anything about you, let alone your political party, we would use the mean, or the average, to predict what you would be. So not knowing your political party, we would expect the number of hours someone watches per day to be on average to be 3.32 hours. Okay. However, there's a problem with again how this is measured. Okay. So this is why you go, well, how do I represent a 0 to 7 increase in political party? Isn't that just becoming more or less Democrat or more or less Republican? Okay, so this output really is not great. It's kind of confusing. You go, so if I have an increase in political party, what does that mean? I'm becoming more Republican? That means I'm actually watching less TV. So what I would do is I actually would recode a variable like this into just Democrat versus Republican to see if there's a difference between the TV that each member of each party watches. Okay? So again, that's why you have to code your variable in a way that you can understand, because OLS regression literally runs numbers or quantities, and if it sees values of 1, 2, 3, 4, 5, 6, 7, it's going to think that a 1 unit increase is going from a 1 to a 2 to a 3 to a 4, a 5, a 6, and that may literally not be what's happening. You're maybe just changing category membership. You're not really increasing in something. Okay, so that's why recoding matters. Okay, let's start with another example though. Okay, so here are two interval variables. So every dependent variable when you run linear regression has to be a quantity, it has to be interval. But what if we had a independent variable that was also interval? Okay, so what if we wanted to know the same thing, predicting how much TV somebody watches, but now we want to know how many kids they have. We think they're related, we don't know, so we're going to test it. So the number of kids they have is interval. It's a quantity. You have 0, 1, 2, 3, 4, 5, 6, or you could call it ratio. It literally starts at a true 0 point. 1, 2, 3, 4, 5. You can have negative children. And then the number of hours of TV you're watching is also a quantity. It's interval. Okay, so these are our two variables, and we can put it usually as is. That's what's kind of nice about using interval data, is you usually don't have to recode it. Okay, you might do so to maybe deal with missing data, but otherwise you just leave all the values as they are and you can stick it right in SPSS because the number inside the variable is the quantity that you want to know. So if we put that in SPSS, this is all from General Social Survey data, by the way. Number of hours per day watching TV, number of children, we get an R squared. I realized we didn't talk about what R squared meant up here. This little R squared from the political party example, that means I'm not covering much of how much TV watching I can explain by just knowing their political party. It's like 1% of knowing their party can help me explain, how many different, varied answers people can give on how much TV they're watching. So it's not a very strong predictor of how much TV you're watching. Okay. Again, down here, also not a terribly strong predictor. It's a little better than party, but it's not contributing much to all the variation that people can give me in their answers of how much TV they're watching. I'm not getting a lot of coverage with it, basically. Okay, so let's look at these pieces again. With an interval variable, number of children, okay, it's going to be a strict numerical interpretation. So we see over here that it is significant, highly statistically significant. We have a slope that goes with this line. It's a positive slope, it's not negative. Okay, so again, the b, or the slope, is the size of the average difference in the dependent variable that corresponds with a 1 unit difference in the independent. So literally, this is what this little 0.189 means. It means for every 1 unit increase in the number of children a person has, so for every additional child a person has, there is a predicted 0.189 of an hour increase in the number of hours per day of watching TV. So for every additional child in the household, we get 0.189 hours, or an extra 11.3 minutes of TV per day. Okay, the relationship's significant. There is an actual linear relationship between how many children you have and how much TV you watch. Okay, so again, those coefficients, that little slope, is interpreted as the predicted value in y for each 1 unit increase in x. It's always a positive 1 unit increase. Okay, let's go to the constant. Give you some practice in that one. The constant is 2.613, so again, on average, we would expect the number of hours of TV you're watching is about 2.6 hours. Okay, it's important to keep track of the units of analysis. So remember, we do the TV watching in hours, we do number of children in actual children they have. So you have to know what a 0.189 is. It's 0.189 of an hour. Okay, you have to know that. So that way you can literally tell someone what it is. And 0.18 or 18% of an hour would be, 17 minutes. Okay, so then you can put it in actual terms. Okay, what if we had a combination of a bunch of stuff? So we have that same famous interval variable, and we have some interval variables, we have some nominal variables, and we want to answer some new questions, okay? So what if we wanted to know, does a person's age, opinions on premarital sex, and whether or not they have a college degree predict the number of children a person actually has? We would think those things are related in some way. We actually have 3 variables: age, how they feel about premarital sex, and having a college degree, that we think relates to, how many children they end up having eventually. Okay, so our main variable is usually the very first one we see, the person's age, okay? And we want to know if that predicts the outcome, how many kids they have. The control variables, just some other things we think also matter, how they feel about premarital sex, whether or not they have a college degree. Those are our control variables. And remember, a control variable is just another independent variable that we think also matters. Okay? You get output that looks like this. So look at this. In the coefficients box, you actually get a little stack of all those variables. And each of those variables have their own coefficient, their own little b, or slope, contributing to that line that helps us explain the outcome, or how many kids people are having. And they each also come with their own significance level. Some of them are going to matter on the line, and others will not matter or contribute to the line. Turns out all of them do, which is kind of cool. And again, at the very top here is that famous constant of kind of our average starting point. Okay, so let's start with these little slopes, these little coefficient numbers. This tells us how the relationship works. So B, our focal relationship, the main one we're concerned about is age of respondent, how old somebody is and how many kids you have. Well, if we look at 0.038, that everything in this B box is the dependent variable, okay? Everything in the B box is the dependent variable, and basically kids increasing or kids decreasing, okay? So just remember that all relates back to what the outcome is, okay? So we have a negative 0.481, we have a 0.038, and we have a 0.437. So let's see what these literally mean, okay? So right up here, for every 1 unit increase in a person's age, for every additional year they are older, they gain an increase in how many kids they have. 0.038 of a child, which sounds kind of creepy, but that's literally what it is. We don't usually write about people having portions of a child, but they're increasing eventually in how many children they're having, okay? So in other words, age is measured in years, how old you are. For every 1 year a person gains in age, they have an additional 0.038 of a child. So I guess if you are an additional 30 years old, you'd have a whole child, okay? It is a significant relationship. There actually is a linear relationship between age and how many kids you have. Obviously, there's a time factor going on there. It gives you more time to have kids, right? Well, now let's look at the little slopes. And this is just a reminder of what the interpretation is. It's always the same. A 1 unit difference in X is this change in Y. Okay, so a 1 unit increase in age, 1 year, amounts to this many more children I have. Here are the B's or slopes on the variables. So again, we talked about how you can't just stick an ordinal variable like opinions on premarital sex in there because it's hard to interpret a quantity of opinions. And we can't just, put also their education in there because that's also an ordinal variable. We can't really quantify what some college means because we don't know what it literally means and how many years they've been going or how much education they completed before high school. If they maybe have less than high school. We don't know if it's 3rd grade. We don't know if it's 8th grade. So often you have to go in and recode these variables into something that you're interested in. And you can recode them in tons of ways. You can make all kinds of comparisons. So on the premarital sex variable, we decided to organize that one into just 1, yes, I think it's wrong, 0, no, it's wrong only sometimes or it's never wrong. So meaning you have a more relaxed opinion on premarital sex. For the college degree variable, we kind of just wanted to know, do you have one? Yes, or don't you? No. So if I have these kind of categories juxtaposed to each other, where we're kind of pitting one against the other, yes, you have it, no, you don't, we can actually easily interpret that because when we do a 1 unit increase, our famous 1 unit increase or 1 unit difference in X, all the 1 unit difference is going from a 1 to a 0. That's it. It's just literally changing from one category to another. So that's why we like them organized that way. We want to know if the presence of this is different than the absence of it. Is having this criteria making a difference? So that's what we want to do with the 1 unit change, going from 0 to 1. Okay, so going back to these famous coefficients over here. So we have college degree people, negative 0.481. We have the premarital sex is always wrong people versus the people that think it's fine with 0.437. Okay, so let's look at what those literally mean. Coefficients for the dummy variables that are just measured with zeros and ones represent the difference between the group presented by the dummy variable and the group you're comparing to, or the omitted group, the zeros. We call them the referent group, the people you're comparing or referring to. In this case, we're comparing those who think premarital sex is always wrong against those who do not. We're also comparing those with college degrees against those without college degrees. So the coefficient, the 0.437 on the premarital sex variable, essentially is this. People who think premarital sex is always wrong have a 0.437 increase in the number of children they have compared to those who do not think premarital sex is wrong. In other words, they tend to have almost half a child more compared to those that don't think it's wrong. And there might be something to that as far as how people think about sexuality, different protections they take in preventing pregnancy and so forth. Okay, it is a relationship that's significant. It has those famous triple zeros. Okay, now let's work on that negative 0.481 that we saw. Okay, sorry, I got my email going off. Negative 0.481, that's a decrease, okay?